Hello. In today's discussion, we're going to be looking at using the binomial probabilities that we calculated in a prior topic in order to construct distributions from binomial situations. Once we have the distribution, we ask the natural questions: what are the average, the mean, what's the spread, the standard deviation. As an introduction to this topic, I'm going to ask you to consider the following preview question. In the town of Helena, about 52% of the days a year are sunny. Over a 6-month period, say 180 days, how many days would you expect to be sunny? So if you want to try it for yourself, pause the video now. Otherwise, I'm going to begin to talk through it. In order to calculate, all we need to do is take, so if I want to calculate the sample average, well, actually, I would just use S. Actually, no, we use average. Is going to be over 6 months, 180 days, well, 52%, so 0.52 times 180. So if I wanted to find the days I would expect, the expected value we also would call the average. The average over 180 days would be 52% of 180 times 180. I'm going to get about 93.6 days. So between 93 and 94 days is what I would expect. And this is how we're going to calculate the mean for the binomial distributions that we come upon later. So hang your hat on this idea, hold on to it. To start, we're going to make a binomial distribution. So in this survey, 60% of adults like texting because it is quicker than calling. 6 adults are then randomly selected and asked whether they like texting because it is quicker than calling, so they're testing this assertion. Create a binomial probability distribution for the number of adults who respond yes, if we assume that 60% think that it's going to be quicker to text, so they prefer texting. Well, N would be how many people we sampled. We sampled 6 people. There's a 60% likelihood that we're going to get them responding favorably to text, which means 40% failure. Failure meaning preferring text or probably calling over texting. X is how many people are going to respond. So between 0 to 6 are going to respond in favor of texting. What's the probability, or what do we expect to get for 0 responding in that way? Well, it would be a binom. N would be 6, P would be 0.6, and X would be 0. So I'd grab a calculator, I go to second distribution, and then I would choose a binom PDF, binomial probability. There are 6 trials, percent, 60%. I want to know when is it going to be 0. What's the probability of getting 0 responding in that way? It'd be 0.004. So 0.004. Then I repeat the exact same. What's the probability that I only get 1 responding favorably to texting? Grab my calculator. I'm just going to recall the entry I did prior. The only thing I'm going to change is X to be a 1. Probability of getting 1, slightly higher, 4%, 0.037. Then I fill in the rest, same exact thing. I just do it for 2, then 3, then 4, all the way up to 6. Now I have a distribution. I can read this distribution by saying, I expect there is an 18.7% chance that 5 are going to favor texting over calling based on the expected 60% for each person. I can then use this distribution to construct a bar graph. Frequency, this is a probability chart though, because we're doing probability. So the first one, 0.004, that's barely negligible, so be that. Next one's 0.037, so 3.7%, somewhere right around there. 2 is about 13.8%, so right around the 14, so I'm just sketching it, be right in there. 3, 27.6, about that. 4, 31.1, about there. 5, 18.7%. 6, 0.047, just below the 5% mark. And there would be my distribution. I can see there appears to be, the average is somewhere around here. And I can then see, the general distribution of it. So that's how I construct a probability distribution for a binomial situation. Calculate each, plot them. Going to give you a chance to try it. So, as a researcher for Barnes & Noble, you'll conduct a survey that indicates 41% of women in the U.S. consider reading their favorite leisure time activity. You randomly select 4 US women and ask if reading is their favorite leisure time activity. Create a binomial probability distribution for the number of women who respond yes. You expect to respond yes. So fill in the chart, pause the video now, give it a chance, come back and see how you did. Here's what you should have calculated. You should have got 12% chance of getting 0, 34% chance of getting one of them saying that reading's their favorite leisure time activity, 35% chance you're going to get 2, 16% chance you're going to get 3, 3% chance you're going to get all 4. Once you've calculated a distribution, a histogram, one also cares about being able to find the average value and the spread of the data. For a binomial distribution, these are shown below. Let's do the average first. The average is the mean, and we did this in the warm-up. In order to find the average, I take my probability and I multiply it by how many trials that I'm running. That's what we did when we were calculating the average number of days we'd expect to be sunny if we knew how many days that we were counting, and we knew the probability that any day would have been sunny, any random day. Then shown below is the variance and the standard deviation. The variance is used to calculate the standard deviation. The standard deviation is what we're going to actually be using. The standard deviation for a binomial distribution is the square root of n times p times q. Number of trials times probability of success times the probability of failure. And almost always, if I can derive something and show you where it comes from, I would do so. But in this case, to derive the standard deviation for a binomial distribution takes some serious math. I'll just show you a quick preview. If you ever take a college-based statistics course, you'll most likely do it. But in order for us to do it, it would take us multiple days just to go through the notation. You can see just to get to both of those, the mean and the standard deviation takes 16 pretty involved steps. So we are just going to be using the result. Using the result, we're going to go back to the situation we were interviewing people about their preference of texting over calling and calculate what the mean and the standard deviation should be. The mean is going to be equal to n times p. N is we were surveying 6 people, 60% chance any one of them would respond favorably, so 6 times 0.6 is 3.6. So the average would be 3.6 people we'd expect to respond favorably. And if I look at where 3.6 is, 3.6 is right here, and that looks to be right around the average because this is a fairly symmetric distribution. The standard deviation is equal to the square root of n times p times q. In this case, it'll be the square root of 6. Probability of success is 0.6 times the probability of failure is 0.4. Grab your calculator, type in square root 6 times 0.6 times 0.4, and you get 1.2 people. If you interpret that, what it means is that on average, out of 6 adults, 3.6 are going to prefer texting over calling. That's what we expect because it's quicker. The standard deviation shows us that most samples of 6 adults differ from the mean by 1.2, which means the majority of the data are going to be between 2.4 and 4.8. Where did I get that? I got that from taking the mean, 3.6, and the standard deviation tells me if I go above it by 1, so one standard deviation above would be add 1.2. That's where I get to 4.8. If I go below the mean by 1 standard deviation, subtract 1.2, I get 2.4. If I am within 1 standard deviation, I'm in between 2.4 and 4.8. That means I should capture the majority of the data. And if I look, 2.4 is right here. 3.8, was that the other one? Oh, 4.8. Be right about there. This captures the majority of the data. The majority being more than 50% of the data. That's why we care about the standard deviation. It gives me the middle value range. I'm going to try one more, then I'll give you a chance to try. We're going to go back to the Helena temperature and sunny day example, but we're going to just consider a month. So in Helena, about 68% of the days in June are sunny. This is a higher percentage because June tends to be a sunnier month than the year as a whole. Find the average and the standard deviation for the number of sunny days during the month of June. Interpret the results and determine any unusual values. N is equal to how many trials we're running. Well, in June there are 30 days, so it would be 30. Probability of any day being sunny is a 68% chance, which means there's a 32% chance of failure or not being sunny. The mean is going to be n times p, 30 times 0.68. Grab a calculator, type that in. and I get 20.4 days. So an average June is going to have about 20.4 sunny days. Standard deviation is a square root of n times p times q would be 30 times 0.68 times 0.32. Square root 30 times 0.68 times 0.32. I get 2.55. We'll call it 2.6 days, which means if I add 2.6 days to 20.4 and subtract it, I'll get my middle range where I'm going to capture the majority of the data. And that's how I'm going to interpret. So my interpretation, on average, there are 20.4 sunny days in June. With a standard deviation of 2.6, most Junes would contain between 17.8 and 23. I got 17.8 by subtracting 2.6 off of 20.4. I got 23 from adding 2.6 on to 20.4, and this gives me the middle range. So most Junes are going to contain between 17.8 and 23 sunny days. Unusual values. Unusual values using the standard deviation are any values that are more than 2 standard deviations away from the mean. That's what we consider to be unusual. So if a June had less than 15.2 days, where did I get that? I took 20.4, my average, and I subtracted off 2 standard deviations. 2 times 2.6 is 5.2. If I subtract off 5.2, I'm going to get to 15.2. Likewise, if I add 5.2, which is 2 standard deviations, to 24, I get 25.6, which means if I have any June that has less than 5.2 sunny days or more than 25.6 sunny days, I'm going to consider that to be unusual. What we're really looking at is, if I imagine this as more of like a smooth curve, a bell curve, my average right here is at 20.4. 2 standard deviations away is going to be somewhere about out here. This occurs at 25.6 days. This occurs at 15.2 days. If I have anything that is more than 25.6 or less than 15.2, that's too far away from average. We'll consider that to be unusual June. So this gives me a nice range of values that sets the boundary for where unusual values would start to occur. We'll preview that more later, but this is just introducing that. Going to give you a chance to try. According to a theory in genetics, when tall and colorful plants are crossed with short and colorless plants, the resulting plants will be tall and colorful about 56.3% of the time because they happen to be the more dominant. If you did such a cross to produce 50 new plants, state where the unusual cutoff values would be, the low and the high, for tall and colorful new plants, to maybe see if there might be something else going on. So give it a chance. Come back after you've had an opportunity to try it, and we'll see how you did. This is what you should have calculated. You should have found the average would have been 28.15, standard deviation of 3.5. If I double 3.5, I'm going to get to 7. So if I am more than 7 above the mean, if I take 7 and add it to 28.15, I get 35.15. If I take 28.15 and subtract 7, I get to 21.15. If I have less than 21 or more than 35 of those plants that are what did I say? That we're going to be tall and colorful, that would be considered to be unusual, and there might be something else going on that I would investigate. So this allows me to determine what the unusual cutoff values will be. And that is it for today. Thank you very much, and have a good day.